relatively cheaply to devices, and so it would scale pretty widely. And it could generate continuous inputs, which would give a very big, a very rich data for analysis of this kind. So I have a project which is funded by the European Research Council, which is related all with automated sound-based diagnostics. So the aims of the project are to collect large data sets, possibly in the wild. Cardiovascular, respiratory, digestive are the areas that we have mentioned in the project. There are not very many large data sets. And as we know, if we want to do machine learning, we want to do analysis of this kind, we do need that sort of data. And we need that sort of data in environments where we can possibly then make the algorithm become more realistic to deal with. And we want to build models which are robust to all these things, which would hopefully create solutions for screening a disease, screening a set of diseases, classification of a specific disease, progression of disease, or even emergency response. You really got to see a doctor now. Integration on device and wearables is something I'm interested in. Offer multi-sensory augmentation, considering that it's not just the sound that could be indicative. You could add other sensors to augment the knowledge, and of course, continuous monitoring, especially for some of the diseases. The project is very, very large in terms of aims. And one of the other aspects which are really interesting, I don't know if we'll manage to touch it, is the interpretation. So we don't want this to substitute the clinical world. We want doctors in the loop, and for that, possibly incorporate techniques that would allow uncertainty estimation and interpretability in the modeling. And that would be really a useful aspect of the whole general project. We are not new to using sound for diagnostics. In my group, this was a project we did 10 years ago, and it was about using Nokia Symbian phones, which are beautiful devices, by the way, because they have very good power. And we developed an emotion sensing from voice algorithm, which would use Gaussian mixture models to map the voices immediately on device and collect information about the emotions of the speaker. Since then, of course, things have moved on. This is not our work. This is work about voice analysis. So it's not just about sounds like hearts, but it's also about voice. Voice can be indicative of diseases. And this was an MIT Technology Review article of January 2017, where they said, well, post-traumatic stress disorder, or even heart diseases could be detected from changes in sounds and pitches and frequencies of the voice. A colleague of mine from the University of Washington has this work where they use 999 codes for the detection of signals of cardiac arrest in the voice using agular breathing biomarkers. And they also try to augment this with noise, so they could show that actually they could use it with an Alexa, for example, or with a device that is in your house that collects your data. So voice is something that has been really studied started to be studied as a symptom, as a sort of source of possible disease interest. In addition to voice, obviously we are very familiar with the fact that doctors listen to our hearts. Unfortunately, one thing I learned by working with the doctors is the fact that heart sounds are almost, auscultations are very difficult to do for human beings. Some consultants get trained and learn how to do it, but now it's almost all substituted with echo, with visual, the picture you see on the right. And but there are reasons why perhaps collecting sounds from the heart in a cheap and automatic way might be still a very good thing to do if we can develop algorithms for that. The fact that in all of this, respiratory and cardiac, there is very limited data available to train algorithms and to develop techniques. There are few data sets around that we've been looking at and contacting people for. And so here, there is an immense opportunity for the community to get together and start collecting this sort of data. The doctors generally train each other by listening to the same patients, rather than perhaps having a big repository of useful data which perhaps they could train. I think some groups are doing that, but there's so many. One of the problems we find is that the ability to choose to understand if from a certain sound, disease X could be diagnosed is a question that is difficult to answer for doctors, because what the human can hear well or less well might depend on the ability of the human ear or the conditions, while a machine might be able to do a lot more. Not only a lot more, but if we start collecting data from continuous sensing, then the kind of disease detection that we can do is different from what a doctor could do, because a doctor wouldn't be there listening to you all the time. And so we're kind of hoping that the discipline can change with the kind of data and algorithms that can build around it. Now, you're probably now sitting there thinking, why is she talking in this session about COVID? And I don't know if you have general questions on this area, but the next thing I'm going to do is COVID and explain how this all fit in. I will wait for Monica to tell me if there are any questions. Okay, I think I will proceed. So we were in the middle of this project trying to work with hospitals and set up data collection mechanism, trying to understand how to do things. and we still are doing that when COVID happened. COVID is a respiratory disease. And that means that perhaps there's something that the project could do. So this is a review of respiratory sound analysis, automatic respiratory sound analysis that you find online. And this is just an example of how people have started working in developing algorithms that can automatically detect or screen, classify categories of diseases, progression of diseases, and so on. And so we have launched a website, which is covid-19-sounds.org. And together with my collaborators in physics, Pietro Cicuta and Andreas Flotto, is a professor of respiratory biology and research director in the Cambridge Center of Lung Infections at Papworth Hospital, we thought that a data collection for COVID was a right thing to do. And so on the webpage, we have developed 2 apps plus a web app, which have been released in the last months. And we have advertised the data collection widely. And this is how, this is the iOS app, how the iOS app looks on the screen. So we asked users to crowd-send, so to send us their data about the breathing. So you're asked to breathe in and out deeply 5 times in a quiet environment and record the data. Data is sent to our service. Then we ask the user to cough 3 times. Then we ask the user to read read a sentence on the screen. I hope my data can help manage the virus pandemic. So, and then this data collected together with medical history and symptoms as indicated by the user. What I'm doing, of course, we are still in the phase where we are collecting data, and I can tell you a little bit about the statistics of all this. So at the moment, 1,000 users have contributed data, and obviously only because very few people have been tested in the world, really. Our data set at the moment only contains about 100 who have been tested, who said that they have been tested positive. You see the growth curve on the top right corner. You see the growth curve of our data. The data collection started in April and went on, well, it's still going on, but it's roughly how it's going. You see it's going as well, because of course, all these things have a sort of life cycle. At the bottom, you see the age range of our participants, and you see the countries that the participants have disclosed they are from. The participants have a chance to say that they don't want to disclose their location, of course. And P and TS means prefer not to say, so they also can say they don't want to share their age or anything about that. The next 2 graphs show the medical history and the symptoms. So this is a medical history graph that shows that this is just from one subset of the data, which is from the Android app. It shows the various top diseases. Many have high blood pressure, and the first line that shows a junction between 2 points is asthma and high blood pressure. Those are 2 symptoms indicated by the same user, and that counts as the largest couple of symptoms indicated in our medical history. This is the symptoms of those who have not tested COVID and the ones that have been tested positive for COVID. And of course, one thing I should say is that we don't know if the people who have not been tested positive for COVID don't have COVID, because a large majority won't have been tested. So there is an important thing to consider when we look at this data. I'll tell you later what we've done to understand a bit better how to get around that problem. What I would like to notice from this graph is that there is an interesting symptoms that comes in the list of symptoms that indicates perhaps the data we have about COVID tested is a reasonable data. The smell and taste loss, which, as we know from the news and from doctors, is a typical symptom of a disease, of COVID disease, is there and is not there in the other data set in terms of symptoms, in the data set of non-COVID tested patients. So we think our data is reasonably sound. Of course, people can say, can lie on our app, but we hope that statistically we have reasonable data set. So from there start to be a number of papers, and this is an example of it, indicating that perhaps the COVID cough is something that could be diagnostic. It's something that has some features that could be considered having some diagnostic features. And this is an example, this is a spectrogram of our data, and following some indication of a researcher, Rita Singh in CMU, as reported on a Forbes article, and also I think on a blog page, that the COVID cough has some low frequency oscillation in the spectrogram, and I have the largest indicate this there. And a healthy cough has, for example, vocal folds after the cough, but has high spread of energy when you have a wet cough, bottom right spectrogram there. You see the vocal fold is very distributed. The energy spread is very distributed when you have a wet cough. And so given this sort of indications and the fact that we have breathing information as well as and the voice, we are now set off to try to analyze the data we have. We haven't gone very far. There is a preliminary paper we put on arXiv now that describes our effort and describes all the details I just described. So it's all open and out there. Our initial testing has taken cough and breathing, our data, as extracted features like MFCCC and split participant for analysis, and we have trained some very basic models and tried to see if we can distinguish COVID tested patients from non-COVID tested patients. Now here's the caveat. We have considered in our data set patients that, for users that have, tested, they were from countries where at the beginning of April, COVID was not prevalent at all. So, for example, Greece was one of those countries at the time. So, we consider most of the users that we consider healthy, let's say, from that country at that time. Our trying to get into hospitals and try to get a better data set of, positively tested and healthy patients with ground truth of perhaps proper tests done over our data. So, there are lots of caveats there. But we start seeing a sort of indication that the breathing and the cough together have some sort of positive signal in understanding that perhaps some person should be tested, or it could have COVID in a way. This is really an initial result showing that we can distinguish with very, not very precise measure COVID tested versus non-COVID using cough and breathing, and COVID tested with cough and non-COVID with cough. So we try to say if someone has indicated they have a cough, will we be able to better distinguish the two? Can we distinguish an asthma from a normal cough? And there's a lot we can do. I will not defend these results very deeply. Progression. One unique feature of the data we're collecting is that in the apps, we ask users to come back to the app every 2 days to give us more samples. So for single users, we might have, if they are really loyal to the app, we would have about 2, 3 4 samples for them. So we could see progression. We could see that perhaps they are developing COVID if they say they have tested positive and then they test positive. We have the coughs before and after. We have the voice before and after. Voice is something we haven't touched in the analysis at all. There are lots of challenges with voice because the voice in environments, everyone is collecting the data differently. There are people with different accents, people with from different countries. So it's a big challenge there, but we start having some interesting data. There are various groups that are working towards this sort of audio challenge. We are by no means the only ones, but I think we have the largest crowdsourced data set collected in this period that I believe have data of this kind. We hope everyone can contribute and spread the word. Here's the webpage. One important notice is that we're trying to openly release all our models, all our papers, and the data with the university to understand how to put together agreements to share data for academic purposes. Our privacy policy and our consent is clearly stating that we would like to do that. And we hope to be able to, we don't want to be online because data, this kind of data is very sensitive. You have voice can be used to recognize people. And even if you don't have an ID for that particular voice, it could be used. Therefore, we'll have to do this via agreements. But we hope to be able to help the community this way reasonably soon. And with this, I think I will finish my presentation and stop sharing, and maybe I can answer some questions.